A very good morning to all of you. In today's class, we are going to discuss dynamics of rotation. In dynamics of rotation, we will cover the topic of torque and angular acceleration of a rigid body, how they are related for a rigid body, angular momentum and its conservation. You can see previous 2 or 3 videos because they are in continuation with the topic of rotation. So let's consider torque first. So this is a familiar wrench. It is used to tighten or loosen the nuts and bolts. Now consider a wrench here where we apply a force F in a direction which is perpendicular to the shaft of the wrench. So we are taking a peculiar or a particular direction of the force. Please note. This will induce a rotation in the nut about its center. The distance from the point at which the rotation about which the rotation is induced to the point where the force is applied is L. Therefore, the twisting effort is directly proportional to both force and distance L. And therefore I can define torque or moment of force F with respect to point O, which is this point, as tau is equal to F into L. Tau is a Greek alphabet which we use to represent the twisting effort of a force, which is nothing but a torque. Generally, physicists prefer to call it a torque. Engineers prefer to call it a moment. So please remember the difference. Definition remains the same. Tau is equal to F into L. Some important points about torque we must always remember whenever you are calculating. Torque is always measured about a point. So it's very important that whenever you are calculating torque, you have to measure it according to some point. In our case, this point is about which the rotation is being induced, and that point is O here. Okay, but it can be, in general, it can be any point. We will see when we solve the problems, we will see more details on that. Then we often use a phrase in terms of torque calculation, and that is called as line of action. The line of action is nothing but the direction of force vector, the direction in which the force vector is working. So in my diagram, force vector is working along this direction. So this is my line of action. I've shown it with a dotted line. Then another concept that you often hear is concept of lever arm or moment arm. The moment arm in my diagram is this distance L. It is the perpendicular distance between the line of action and point about which the torque is calculated. So this is my line of action. This is the point about which I will calculate my torque. So if I drop a perpendicular from this point to the line of action, then this is my lever arm. This distance is my lever arm. Remember, I do not use the lever arm phrase. We will not use it if this distance is not perpendicular, as we will see in subsequent cases. Now, torque can induce a rotation which can be anti-clockwise or sometimes clockwise, depending on how the torque will induce a rotation. It can be either considered a positive torque if it is producing an anti-clockwise or counterclockwise rotation, or negative torque. Suppose if the force is working in this direction, then the wrench will move this way. This force will produce a clockwise rotation, and therefore the torque produced by it is going to be a negative torque. So we will write it as minus F into L. Now what happens if the force is working arbitrarily? It is not perpendicular to this line. So if the force is not perpendicular to this line, remember I can't call this as lever arm. Let this length be R, and this is the direction of R, this dotted line. And force makes an angle theta with the dotted line or with the direction of R. Then in that case, the force will have two components. One along R, which I may call it as radial component. Remember, if there is a rotation this way, then this line will become the radius or radial line. So component of the force along this line will be called as radial component, which will be, since this is an adjacent side to theta, this will be called as F cos theta. The other component of force, which can be tangential to the circle. Remember this point will undergo circle, and this component is tangential to the circle. So I will call it as F tangential or F tan, and it is equal to F sine theta. So we can resolve this force into two components, F radial component F cos theta, tangential component F sine theta. Okay, now radial component will not introduce any rotation effect. You can see why. The radial components will try to pull this entire wrench in this direction, and it will not introduce any rotation effort. But the tangential component will introduce the rotation effort. So for tangential component, since it is perpendicular to R vector, the R becomes the lever arm. So torque is given by F tan into R, which is F sine theta into R, which is also F R sine theta. So remember, R is a lever arm for F tangential. It is not a lever arm in general for force F. The other way to calculate torque is this. We have the same situation in this drawing. So all we do is we find the lever arm. So what we do is we find the lever arm for force F. So I will extend the line of action of force. This is line of action of force. I extend it. Remember, the force works here. I extended this line towards bottom. I drop a perpendicular from point O to the line of action. This distance R with this distance, which is, I will call it as L. will be the lever arm, will be the perpendicular distance between the point O about which the torque is being calculated to the line of action. Now, if this angle is theta, this angle is theta, then the lever arm is r sine theta. And therefore, I can write torque as F into L, which is F r sine theta. You can see that both the calculations produce the same result, F r sine theta, and here also F r sine theta. But the method we have calculated, they are different. So in solving problems, you can practice both the methods in solving problems. Sometimes one is useful and sometimes the other is very useful. Now, torque is a vector quantity. How would the direction of torque is given? So the direction of torque is given by the cross product between r vector and f vector. Remember, r comes first. So torque tau or vector torque tau is equal to vector r cross vector f. So you know cross product rules. To determine the resultant direction of the cross product, you curl the right hand fingers in the direction from the first vector to the second vector. Remember, the first vector will be the vector which is written first in the cross product. So in my this diagram, my r vector is this way. This is my wrench. R vector is this way. Force is shown by a dot. Whenever I show a vector by a dot, it means it is coming out of the page. So it is towards you as you look at this screen. So you curl the fingers of the right hand from this vector to F vector. So you can see it is curled this way. In that case, the outstretched thumb will give me the direction of the torque. So on this, if I rotate it this way, which is anti-clockwise, then the torque works in the upward direction. If I revert the direction of the rotation, then you can see that torque is working downward. So my wrench R was pointing in this direction. Now the wrench R is pointing in the opposite direction. So direction is reversed, torque is working downward. So do remember two things. Torque is cross product of R and F. Also remember that it is given by the right hand, or sometimes also called as the right hand screw rule. Now whenever the torque acts, the body suffers angular acceleration. So let us try to establish the relation between the two. So consider this diagram. This arbitrary shaped body is rotating about z-axis. So any point on the body is moving in circle about the z-axis as axis, and let's say that r is its radius. Now this point can experience a force which can be resolved into three components. One is the radial component along the radius, one along the z-axis, and one is the tangential component, which is F tan. Now remember, the radial component will not produce any rotation about z-axis. Even the component of the force which is along z-axis will not produce any rotation about z-axis. We are focusing only about z-axis right now. So the only force that can change the state of rotation about z-axis is F tangential. It can speed up the body or it can slow it down. So the torque, so I will imagine that the entire body is divided into large number of small points. and we will take one such small point, which I would call it as ith point. And as we have discussed, there can be three possible forces on the ith point, of which only the tangential force will apply a torque. Therefore, torque applied by the tangential component of the force is tau I is equal to Ri F I tangential. Remember, I in general is on ith particle. It is an index that will run from 1 to n. Now, whenever the torque will act, whenever this force will act, tangential force, it will induce tangential acceleration. We have already studied tangential acceleration in circular motion, dynamics of circular motion. So please revisit that concept. F is equal to ma. So force on ith particle will produce acceleration on the ith particle. Therefore, I can combine everything together. Linear acceleration of the ith particle, which is tangential acceleration, is equal to r alpha, where alpha is angular acceleration. This relation we have derived in two classes before when we did kinematics of rotation. So the torque on ith particle, if I combine everything, is will be given by torque tau is R into F, but in place of F I can write MA, and in place of A I can write R alpha. So if you substitute, you get mr square alpha, and this is written for the ith particle. Remember, for different particle, mass can be different, R can be different, but alpha will remain same for all of them. Because if alpha doesn't remain same for all of them, it will no longer be a rigid body. So this is the torque acting on one particle. Total torque acting on the body is sum of torques on all the particles. So I can run a summation. Torque tau is sigma tau I, which I can run on this MIRI square alpha. As we have just said, alpha is constant for all the particles, so it will come out of summation. You get sigma MIRI square. But this quantity, sigma MIRI square, is nothing but the moment of inertia of the body. We have defined it in the last class. So the torque is equal to I times alpha. So this is for a rigid body. I can always write that torque is equal to its moment of inertia into angular acceleration. This equation looks more or less like Newton's second law. F is equal to ma. So this is replaced by force, this is replaced by linear inertia, and this is replaced by linear acceleration. So this equation is nothing but, we can say it's Newton's second law for a rigid body, rotational analog. Rotational analog of Newton's second law for a rigid body. So whenever a body is rotating and somebody asks you what is the Newton's law for a rotating body, you can use this. Torque is equal to I alpha. Now remember, just like forces, the torque is also can be due to internal and external forces. So I will demonstrate is here in this diagram. So let us say that this is an arbitrary shaped body. Now particle 1 exerts some force on particle 2 this way, and particle 2 exerts an equal and opposite force on particle 1 in this way. Remember, these forces will be equal and opposite because of Newton's third law. Now, about point O, these forces may induce some torque. These torques are going to be called as torques which are internal to the body. So, this is the lever arm and this is the force. So, the torque is going to be the force into lever arm. But look at it, in magnitude, both the forces are equal. Lever arm is common. So in magnitude, both the forces will apply the same torque. Remember, but in opposite directions. Torque due to this is going to be clockwise, so negative. Torque due to this force is going to be anti-clockwise, so positive, and they are equal in magnitude. So when you calculate the total torque, they will cancel out. So always remember that total torque due to internal, when we write this equation, torques are composed of internal and external torques, but due to Newton's third law, the internal torques will always cancel out, and only torques that will matter will be external torque. Do remember. For example, if you are in a vehicle, standing in a vehicle, in a say in a bus, and you push the wall of the bus, say in one direction. So you may apply a torque on the bus. The friction between your feet and the ground surface of the floor of the bus will apply an opposite force on you, which will apply an opposite torque, and both the torques will cancel. So this is very important for us, that only torque which matters, they are external to the system and not internal. Another torque which is often encountered is torque due to the weight of the body. Every body possesses a weight because of its mass in gravity, and it's a force, and it applies a torque. Here this cube's motion is blocked by this small notch. As a result, it will go in rotation. So the weight or the force due to gravity works in the vertically downward direction. So whenever you are calculating the torque of the weight, you have to calculate along the center of mass. Do remember that. So although the weight is distributed, torque is always calculated about the center of mass. Now we go to the last part of the lecture, and that is angular momentum. You know what is linear momentum? Linear momentum of a body is defined as mass into velocity. So if you have a body of mass m moving with velocity v, linear momentum is p is equal to mv. Suppose if you have some point O in an inertial frame, and the position of body is vector r with respect to that point O, then we can define angular momentum L as r cross p, or it can also be written as r cross mv. So this is angular momentum. Angular momentum is can be defined as moment of linear momentum. The magnitude is straightforward. The magnitude can be defined as mvr sine phi, where I have a diagram here. My particle is at this position. Its linear momentum is pointing in this direction. So P is equal to mv. My my axes are here: z axis, x axis, y axis. Origin is this point. Now position of the particle is given from the origin in the form of vector r. This is the line of vector r. So angle between r and p is phi, let us call it. So the L can be given by angular momentum is mvr sine phi, which is an expansion of this term. M is a constant. R cross V can be written as V into R into sine phi. Now, just like in torque, here also we can take the line here, line of P, and extend it at the bottom and drop a perpendicular from point O to that line. Now, if this angle is phi, this angle is also phi, and if this angle is phi, then this side is r sine phi, and this is called as lever arm L, or technically I can call it L as r sine phi, and then angular momentum L can be written as linear momentum into this r, lever arm L. What will be the direction of L? So remember, it's a cross product. So you have to curl your right hand finger again from vector R to vector V. So this is my vector R direction. Start curl. First, keep your right hand palm stretched in this direction, and then you curl it towards P. A curl is towards V, this way. So when you curl it, the outstretched thumb will give you the direction of angular momentum vector. So the direction of angular momentum vector will be this way, that is along the z-axis. So remember again that the L vector, just like the torque vector, L vector is perpendicular to the plane in which R and P vectors lie. In this diagram, R and P vectors lie in xy plane, and L vector is along the z-axis, which is perpendicular to xy plane. Going ahead, now I have angular momentum. Let me take the time derivative of this. That is, I want to find out the rate of change of angular momentum. Now, when you take the derivative on the right hand side, we have to apply the product rule. So, dl by dt is given by derivative of r into p, which is mv, plus r into derivative of p. So vector r into derivative of p, which is m is a constant, its derivative of v with respect to t. Remember, this product is a cross product, so that will sustain throughout the derivative. So you will use a cross here, you will use a cross here. Now dr by dt, r is a position vector. A rate of change of position vector with respect to time will give you the velocity vector. So this is going to be v. Now rate of change of velocity vector with respect to time will give you linear acceleration vector, which will give you a. So it can be written as v cross mv plus r cross ma. Now m is a constant or scalar quantity. So v cross mv means it's actually v cross v. But what is the cross product of a vector with respect to itself? The cross product of a vector with respect to itself is always zero. If you don't know, find it out how. But this term will reduce to zero. Only surviving term is this. Ma is nothing but the force. So this can be written as R cross F. But R cross F is, we have just defined. It's the torque acting on the body. So what does it mean? It means the torque acting on the body is equal to dl by dt, or rate of change of angular momentum. So remember, this is another equivalence of Newton's second law being written for the rotational motion. We have written the second form of Newton's second law as force is equal to rate of change of linear momentum. Here, torque is equal to rate of change of angular momentum. So, rate of change of angular momentum of a particle equals the torque of the net force acting on it. Now, how do we find the angular momentum of a large rigid body which has large number of particles? So that is a fairly straightforward procedure. We divide the body into large number of particles having masses m1, m2, m3 dot dot. Each particle having distances r1, r2 from the axis of rotation. We can again use the index I that as we had used earlier. The magnitude of the angular momentum of ith particle. Now we can use whatever we have developed so far. So the magnitude of angular momentum of ith particle is mvr, but v is nothing but r omega. So mvr will become m r omega into r. Remember, we are writing all for the ith particle. Once you open the bracket, you can write it as mi square omega. So this is the torque acting on the ith particle. What is the total angular momentum of the body? So you make a sum of this for all the particles. You have n number of particles in a rigid body, tightly packed. So you have to sum this over all the particles. So once you do that, you get L is equal to sigma Li, which is equal to sigma mi square. In bracket, summation will only go over mi square. Omega remains same for the entire body. Why? Remember, the body will no longer be a rigid body if omega is different for different bodies. So the quantity in the bracket here is nothing but the moment of inertia. So the angular momentum L in magnitude can be written as I times omega. I is the moment of inertia, omega is the angular velocity. This is how we write L for a rigid body. What about the direction? So in the vector form, we write this equation this way. Vector L is equal to I times vector omega. So that's a very straightforward. I is a scalar quantity. Omega, vector omega is vector. Whatever direction omega will take, L will take the same direction. So do remember, in the diagram it will look like this. Remember that direction of omega is given again by the right hand rule. You curl the finger of right hand in the direction of rotation. Outstretched thumb gives you omega. L will have the same direction as that of omega. Remember. Here, if omega is reversed, L will also get reversed. At this point, I would like to say you something which is very important. As you study physics more, you will find that the angular momentum is going to play a very important role. When you do quantum mechanics, nuclear physics, or even higher classical mechanics, the angular momentum plays a very, very important role. In fact, entire chapter of rotation is very important because even in molecular dynamics, uh, atomic spectra, everywhere you get entangled with rotation of bodies. So please master this chapter very thoroughly, both theory, concept, and problem solving, because it's going to be very, very important. And it is, I would say, a little challenging chapter also. You should have done your Newton's laws well, you should have done your vectors well to understand the concepts in rotation. So see to it that you give enough time and energy to this chapter as you prepare towards your forthcoming exams. Then we come to the famous theorem of conservation of angular momentum. When the net external torque acting on a system is zero, the total angular momentum of the system is constant or it remains conserved. I have a very simple proof. For a more detailed proof, you can refer to the book. So the torque acting on a body we have seen can be written as I alpha. Alpha is angular acceleration, which is the rate of change of angular velocity. Alpha is d omega by dt. I can take I inside. So it will become d by dt of I omega. But I omega is nothing but angular momentum vector L for the rigid body we have just seen. So the net torque acting on the body can be written as dl by dt, again for the rigid body as well. Now if torque is zero, if the external torque acting on the particle is zero, then dl by dt is 0, and that means L is constant. So this is what is the statement. If there is no external torque acting on the system, then the angular momentum, the vector angular momentum is remains constant or it is conserved. So remember, the angular momentum is conserved both in magnitude as well as in direction. So in magnitude, I can write L is equal to I omega, but since it is constant, then any change in I from I1 to I2 will also include a change in omega 1 from omega 1 to omega 2 so that the product remains constant. So you remember you have done these. So if there is a person spinning on a spinning table with arms stretched, it will have a higher moment of inertia and lower angular velocity. The moment you fold the arms closer, you will have smaller moment of inertia and larger angular velocity. So we are going to take these things in the problem solving. We can stop here. Thank you.